Welcome to the High-Rise Exam Construction Workshop. I'm your chief architect, and today we are tackling one of the most notoriously misunderstood blueprints in Cambridge AS and A-level mathematics. I'm talking about Section 2.1, Algebra. We're going to learn exactly how to lay down an unshakable mathematical foundation and erect load-bearing arguments that can withstand the absolute most intense scrutiny from any Cambridge examiner. Because look, when you're dealing with polynomial division or the factor and remainder theorems, you're not just solving simple equations. No, you are constructing a logical, multi-story framework. So let's look at the schematic layout for today's build. Look closely at this quote. It's straight from the principal examiner reports. They consistently highlight that students struggle heavily right here. We see candidates walking onto the exam site every year with the right tools, but absolutely no blueprint. I see two types of builders out there. You've got Alex, who just stacks too many unorganized factual bricks, right? Just throwing numbers around, hoping something sticks. And then there's Sam, who focuses on a flashy exterior design, maybe writing out a final answer really neatly, but completely forgets the load-bearing mathematical structures underneath. Why is this area so prone to a total collapse? Because polynomial division requires precise, step-by-step algebraic manipulation. One tiny arithmetic slip, and your foundation cracks. If that foundation is weak, everything built on top of it, like your advanced calculus, is just going to come crashing down. Okay, Section 1. The foundation. Connected conceptual understanding. So just like in structural engineering, you literally cannot build a sturdy second floor if your ground floor is made of sand. Rote memorization, it just won't work here. Examiners heavily reward candidates who demonstrate a connected conceptual understanding that actually transfers to unfamiliar contexts. Let's map this out on our digital grid. Making cross-topic connections is absolutely crucial. That means realizing that finding the roots of a polynomial algebraically is the exact same thing as finding the x-intercepts of its graph geometrically. If Alex just memorizes the long division formula, but panics the second a question asks to connect that to finding graph coordinates, well, that mathematical structure simply won't survive the marker's rigorous review. You've got to connect those algebraic roots directly to the geometric graphs. Now, before you erect any of these arguments, you absolutely must heed this major examiner alert. Clearly define your terms. Candidates consistently lose points by confusing key terminology. What do we actually mean by terminology in math? Let's make it super simple. If substituting x equals 2 makes your equation equal 0, the number 2 is the root, but the bracketed expression, x minus 2, is the factor. If Sam confuses those two in a written conclusion, the examiner instantly spots a critical structural flaw. You have to use the exact mathematical language required by the blueprint. Moving right along to Section 2, the procedural framework. When you faced a high-tariff, complex past paper question, you need a procedural sequence to safely stress test your mathematical framework. You gotta follow these 5 systematic steps every single time. Step 1. Deconstruct the question. Are they asking for a remainder? Or are they hiding a factor theorem problem inside a weird geometry context? Step 2. Extract the data. Pinpoint your exact polynomial and your divisor. Step 3. Select the analytical framework. Are you going to use traditional algebraic long division, or is synthetic division more efficient here? Step 4. Execute your notation flawlessly, making sure those text blocks and equations balance line by line. And finally, Step 5. Present terminology. Conclude your math with the load-bearing terms we just talked about. Which brings us to Section 3, the method mark strategy. All right, pause the blueprint. Site inspection. Before we go any further, to fortify your academic foundations and get weekly structural grade upgrades, make sure you subscribe to Ace the Exams at AC Exams right now and turn on all those notifications. Okay, back to the site. If you're like Alex and you just stack unorganized factual bricks to get a quick answer, you are going to fail the inspection. You must show clear working to win those method marks. In Cambridge Math, the final answer is really just the roof of the building. The method marks, those are the steel beams holding the whole thing up. Look at the answer-only approach. You calculate a remainder in your head, write down r is equal to 5, and move on. If that's wrong because of one tiny slip, 0 marks, complete structural collapse. But with the systematic method mark strategy, you explicitly show the steps. You literally write out, let f of x equal the polynomial, substitute x equals 2. Even if your calculator slips and the final roof tile is a bit crooked, the examiner sees your load-bearing math logic is perfectly sound, and you still score the majority of the marks. Now, what happens if you hit an unexpected structural crack mid-paragraph? This is where you step in to weld your evidence to your analysis flawlessly. When evaluating mathematical proofs, you have to identify your limitations. For instance, are you assuming the divisor is strictly linear? Note the assumptions made in your model. What alternative interpretations exist if the degree of the polynomial changes? By addressing these directly and measuring their effect on your conclusions, you apply a perfect structural weld to your arguments. Let's look at Section 4, Critical Analysis and Identifying Flaws. All right, it is time for the interactive viewer's stress test. Imagine a 60-second visual countdown timer right now. I want you to look at a sample student answer and identify the flaw. Ready? A student is asked to compare two different polynomial models. They write a whole paragraph about how both models yield a remainder of 0, making them both factors. Time's up. Did you spot the structural gap? The gap that causes a total mark drop is that comparative analysis requires identifying both similarities and differences. So many students hit a crack here by only listing similarities. But examiners demand that you support each comparison with evidence. Maybe one method reveals the quotient directly while the other only gives the remainder. You have to use your numerical working to logically support those claims. Okay, Section 5, Top 3 Examiner Warnings. We are heading into the final build inspection. Let's look directly at the principal examiner reports for the top 3 red flags inspectors look for. Mistake number 1, vague answers. You can't just write, use the theorem. Which one? Factor or remainder? Be specific. Mistake number 2, forgetting presentation conventions. If your load-bearing math is good, but your presentation is just an unannotated disaster, the examiners simply cannot navigate your site safely. And mistake number 3, ignoring the context. If that polynomial represents a real-world physics problem, your final answer has to relate back to that specific reality. So, ask yourself, are you securing your method marks or just chasing the final answer? Practice these specific past paper techniques, focus on the procedural framework, and make sure your exam strategy is truly built to pass that final inspection. Let's recap our 3 rules of equation engineering for today. 1. Define your terminology to build a solid foundation. 2. Follow the 5-step framework to stress test your working. And 3. Prioritize method marks over the final answer. The next time you face a complex 2.1 algebra question, ask yourself, are you just blindly stacking numbers hoping they don't fall, or are you engineering a mathematical proof that cannot be torn down? To keep getting these structural grade upgrades, subscribe to Ace the Exams at AC Exams, click that notification bell, and leave a comment below with your specific subject and level. Happy building, and I'll see you on the next site.